Hey everybody, we're going to talk really quickly about some linear algebra basics that we all need to know. It's going to feed in just briefly into our discussion of Gaussians, but we're going to build on linear algebra all quarter long, okay? So we need to make sure that everybody's up on the linear algebra. I need to make sure that everybody feels very comfortable with vector addition and multiplication. Also, the dot product operations are very important to all kinds of machine learning. We won't necessarily need any of the other kinds of stuff like cross products that you may also have done in linear algebra. Okay? Let's remind you how this works. So, a vector A, in general, I'm going to try to really keep this notation very constant. A vector will be noted as a lowercase boldface, in contrast to a scalar, which will be lowercase not bold, and a matrix, which will be uppercase boldface. Okay? So here we have our vector A. A, as you can see, is a three-dimensional vector. A is notated by this black arrow, right? Which starts at the origin and goes to this particular place in the three-dimensional space, because this is a three-dimensional vector. This notation right here says A is in the vector space of three-dimensional real numbers. This kind of R means real numbers. We could use a similar kind of font with an I for integers or N for natural numbers, which are equivalent. Mostly, I guess you would see the N, like if they were counting numbers, okay? But most of the time, we're looking at real numbered variables in this class. And to the power 3 or to the third, like superscript, that is an indication of the dimensionality, right? So this is a three-dimensional vector. So the three dimensions are on the x-axis, the y-axis, and the z-axis. And the values of that vector, the x-axis value is going to be the distance in the x direction away from the origin, the y direction away from the origin, and in the z direction away from the origin. Those three vector components, however long ax, ay, and az are, they are going to be our vector, right? So this, you will note, is a column vector. Typically, most of the vectors we're going to work with by convention are column vectors. There is always an equivalent bit of the linear algebra math if we assume that it's a row vector instead of a column vector. So nothing is eliminated here when we talk about column vectors without loss of generality, as the mathematicians like to say. Okay, now, how long is our vector? How big is it? You are very used to measuring this triangle formed in the three-dimensional space. The hypotenuse of the triangle, or the length of the vector itself, is just a squared plus y squared plus z squared, or ax squared plus ay squared plus az squared, right? Take the whole thing, square root it. It's the Pythagorean theorem in 3 dimensions. Not surprising. Well, this notation here, these two lines around the vector and a little 2, that is the so-called L2 norm, or Euclidean norm. A norm is a way to measure the size of a vector norm, and that's what these lines mean. The 2 tells you it's an L2 norm, or a Euclidean norm. That is the Pythagorean theorem. It is one of a set of possible vector norms. In general, I can replace that 2 with any integer n. And the format of this L norm is like you would already expect. All the vector components, right? It doesn't have to be three-dimensional. If it's n-dimensional, if it's m-dimensional, there'll be m additions here, right? And we would put all those things to the nth power and then take the 1 over nth power. And you can see how 2 is just a particular example. The Euclidean norm we are very used to. Okay. So in general, if you just see the vector norm lines without any numbers, just assume we're talking about the Euclidean norm. But you should also know that there are cases and places where it won't be the Euclidean norm, where we will be talking about the one norm, or also called the city block distance. Okay? The city block distance is equivalent to add up ax plus ay plus az. Like, for instance, if you were going all the way around the block instead of cutting straight through the block. The Euclidean norm cuts straight through. The city block or taxi distance or various other names that people give it, the L1 norm, is going on the outside of the block, ax plus ay plus az. All right, so those are two most common norms, the L1 and the L2 norm. Generically, we're talking about the Euclidean or L2 norm. So we can add vectors, right? I'm not going to belabor this, but if we add two vectors together, they've got to be the same dimensionality. All right, so for any two vectors, it's obvious we just add the components together to get the addition of the vectors. And it has a geometric interpretation, which you've been looking at on the screen, that hopefully you already knew. All right, so the dot product may be something that you haven't thought about since linear algebra. The dot product is a measurement of similarity between two vectors. If two vectors are parallel, their dot product is going to be the length of the shortest of the two vectors. Another way to think about the dot product is as a projection. What if you were shining a bright light from right above here down across the A vector? The shadow of the A vector on the B vector would be A dot B. Okay? And if you want to normalize that in terms of how long is the B vector, then you would divide by the length of B, right? That's what this is, the length of the B vector. So if you do A dot B, that gives you a length of the length of A projected onto B. Think of the shadow of A. And then you divide it by the total length of B. What you get is the proportion of the B vector that A vector has in the same direction as the B vector. Okay, so that's the dot product. It's a measure of similarity between vectors. So in general, we can see that A dot B is simply equal to the length of A times the length of B multiplied by the cosine of the angle in between them. You can note A dot B this way, or you can note it this way. They're just two different mathematical notations for the same damn thing. Now, in general, you can also make the dot product through vector multiplication, which we haven't covered in the review yet. But again, this dot product is equivalent to a vector multiplication. So let's talk about matrix multiplication right now. So we've got a vector A. This one's a row vector, right? We could transpose A into a column vector. We might have a B vector that is already a column vector. Note all of these vectors are in the n-dimensional space, the same vector space. So what would happen when we do A multiply by B? This is not a dot product. This is a matrix multiplication. Understand the difference. Well, the generic rule is for matrix multiplication, the first matrix tells you how many rows. The second matrix tells you how many columns. So A has one row, so our answer is going to have one row. B has one column, so our answer is going to have one column. In fact, what happens is we get A1 times B1 plus A2 times B2, blah, blah, blah. So this is a scalar. It adds up. to a single scalar number. In general, matrix multiplication is not commutative. We can't say AB is equal to BA, because in situations like this, BA, well, B is going to determine the number of rows, and there are going to be n rows. And A is going to determine the number of columns, and there's going to be n columns. Whoops, I need to change my notation here. I had B going to 3 instead of to n. Okay, whatever. I think you get the idea. This should be B sub n, and this should be B sub n, and that should be B sub n. So, matrix multiplication. AB is not the same as BA. Okay. What if we're doing matrices instead of vectors? Well, the same rules apply. AB is going to have the number of rows determined by A and the number of columns determined by B. The thing about matrix multiplication or vector multiplication is that we have to have the inner dimensions matching, right? The number of rows here can be whatever it wants to be, but it's got to match the number of columns here has to match the number of rows here. A sets the number of rows, B sets the number of columns, but the opposite ones got to match. There are 3 columns in A, there have to be 3 rows in B. The inner dimensions of the matrices have to match. So that we can do this and get the right number of elements to make a 2-row by 2-column matrix. Okay. One last bit of linear algebra that we're going to use today is the determinant. The determinant of a matrix is a function of all the numbers in the matrix. And the generic idea of the determinant is that we're going to start on one of the diagonals, and we're going to take all the diagonals going from top left to bottom right. So A, E, I. A times E times I. Okay? Then we're going to take another diagonal, B, F, G. Right? That's a 3 diagonal there. Then we're going to take C, D, H. Those are all of the diagonals available in a 3-dimensional matrix. And we're going to subtract out the top right to bottom left diagonals. We're going to subtract out C, E, G and B, D, I, and subtract out F, H, A. Okay, so that's the determinant. In a 2x2 matrix, you can understand the determinant as being the area inside the parallelogram bounded by these vectors, AC, BD. Okay, so the determinant, the interpretation of it, is the area bounded by the vectors in the matrix. Right? So think of a determinant as a scalar that represents the total space covered by this matrix. All right. So let's use that determinant. What happens when we take a normal distribution, which we're used to in one dimension, right? Like height of people, we have normally distributed height. What if we're dealing with probability distributions that are multivariate? It's not one variable like height, it's multiple variables, and our normal distribution is therefore operating in a vector space X, where vector X is a k-dimensional column vector. So maybe those vectors represent something like miles per gallon of a car, top speed of a car, the price of a car, and all the elements of the vector represent those variables about a car. So if we say something is normally distributed in that three-dimensional space, then the vector space X is all the variables, all the rows of that vector space represent those variables. And we have a Gaussian, which in general can have different shapes, right? We're used to this kind of Gaussian shape. That Gaussian shape can be squished or elongated in different ways. How can it be squished or elongated? Well, we need this thing called a covariance matrix, the sigma. The sigma says, hey, how much is the x variable correlated with the y variable, or with the z variable, or however many dimensions we've got. The same way you're used to variance or standard deviation for a single variable, well, we've now got that in all the directions of the vector space. Each variable has its own variability, and there could be correlation between any pair of variables. And that's what the sigma, that matrix, shows you. So in general, what is the distribution in k dimensions? Well, if we put in k-dimensional variable here, and we have a k-dimensional mean, where the mean is in x and y and z and whatever else there is, well, we have this k by k matrix that is the covariance matrix. All right? And this stuff inside is the distance metric you're used to for any one-dimensional Gaussian. So the distance between any given data point and the mean squared. See this? Linear algebra land, baby. This is a square term. Instead of x minus mu squared that you're used to in the univariate case, we've got to keep in linear algebra the right number of rows and columns and stuff. So to get the probability density to be a single number, we've got to take the transpose of the column vector and make, instead of that many rows, we need to make it that many columns in a single row. So that we get a single row, that means a single row on the output. Okay? Then this last bad boy is going to be a column vector, because x and mu are column vectors. So it's going to have that many rows, but a single column. So one row transposed, one column not transposed. At the end of this matrix multiplication, we're going to have a single number for the probability density, wherever we're at in the vector space. Okay? In the middle, so this is x minus mu squared, which you're used to. And then we also have the covariance matrix in the middle. Okay. As always, we have a normalization term. And the normalization term on a Gaussian is just to make sure that the total amount of probability equals 1. So this normalization term, as with our univariate, has to involve the size of the variance. Well, that determinant function, that's the size of the variance, right? So that determinant is now in play here. Okay, so this is the k-dimensional generalization of a Gaussian distribution. Now, let's in general just talk about the idea of vectors as variables. Right? Every position in a vector is going to be a measurement. Maybe for something moving around in space, it would be xyz position and xyz velocity. Maybe for houses, it's going to have each one of the elements of a vector is going to have some relevant measurement of a house. Or for a car, I already did this, right? So maybe for animals, it's like the weight of an animal, the number of legs, whether it lays eggs or flies. So now some of these variables are real numbers, right? Like engine displacement or square footage. But some of these variables are categorical in nature, like color or does it lay eggs. These have only discrete and finite possibilities, and categorical variables are different than real variables for that reason. Okay, so let's go to the animal idea. Here are some animals. Sparrow, does it fly? Yes or no? Does it lay eggs? Yes or no? What is its weight? So for the different animals, we need a way to represent these animals as vectors. So for something which is categorical binary, we can simply fill in true or 1 for if it flies, or false or 0 for if it doesn't. And we can represent true, 0.087 as our sparrow. Okay? Not too hard. However, if there are more than 2 possibilities, like color of a car, well, it could be red or green or blue or yellow or, plum crazy if you're a 1970s Dodge sports car fan. Okay, so how do we represent those colors? Well, we cannot just turn colors into numbers like 1, 2, 3, 4. Because if we did that, there would be some inherent idea that plum crazy was a higher value than blue. And there's no inherent ordering in color, right? There's not a way in which blue is less than plum crazy. That's just, inducing order on something that doesn't have order. And if we do that, various kinds of machine learning algorithms are going to make dumb assumptions if we give order where none existed previously. So how can we represent categorical variables without inducing order? Well, if you think of x and y as one of them being blue and one of them being plum crazy, well, we could take, so let's go to the flying version here, 2 dimensions, right? And these 2 dimensions represent the possibilities of fly. Yes, it flies. No, it doesn't. If this was color and maybe there were 5 colors, then we would have 5 dimensions here for color, and each one of them would be a separate color. This would be the red dimension, yes, red, no red. Then there would be the blue dimension, yes, blue, no blue. Then there would be the orange dimension, yes, orange, no orange. Okay? Every one of the 5 colors we're trying to encode would have its own separate dimension in the vector. And the only possibilities of that dimension is yes or no, 1 or 0. Now, when colors are mutually exclusive and only one of the color's dimensions gets a 1 and all the other colors' dimensions get a 0, that is the so-called one-hot code. For however many discrete possibilities there are for a variable like does it fly, or a variable like what color is it, we have that many dimensions, and the dimensions are orthogonal to each other, the same way x is orthogonal to y. Okay? And because of that, we're not inducing any ordering. So this is the one-hot code, and it prevents machine learning systems from assuming that a given category has an order when it doesn't have an order. All right, so more generally, let's go with, don't care whether these variables are categorical or real valued. We just represent a given x as a feature vector. Okay? What happens when we have a data set where we have an m-dimensional vector that represents every data point, Every data point has m measurements. And we have n data points in our data set. Well, we're going to then take those column vectors, transpose them so that this is the first data point, okay? And this is the second data point, all m of its variables, and so on and so forth. And then we have n rows in the data set. So this is our so-called design matrix. It is a standard matrix representation of a data set, which we will use a lot in the future. All right, so we take feature 1, feature 2, feature 3, and first data point, second data point, and we put their data points and features in like that. All right, that's it. Hey, everybody, hope you enjoyed this. Talk to you in class. Bye.